Hi, this is Mrs. Vrobel. This is part 3. So in the previous section, we were looking at molar mass and how to convert between moles and particles. Now we're going to use molar mass in a different way. This way you're probably a little bit familiar with. Here we have sodium hydrogen carbonate, and you've seen it in your pantry, the Arm & Hammer baking soda. They want percent composition of the compound. Now, what you need to figure out with this type of problem is you're looking at molar mass. So 84.10 grams is essentially adding up the different masses for this compound. Please remember that oxygen has 3 atoms. You want to multiply the molar mass of oxygen 3 times. But you essentially take the individual masses of the sodium, hydrogen, chlorine, and oxygen, and you divide them by the molar mass, and it gives you a percentage. Now, if you notice, if you took each single atom and you added its percentages up, you should equal 100%. If you don't, it's possible that you did something wrong. Okay, let's tie another thing in with molar mass, empirical formula. So with empirical formula, you're going to be doing some calculations with that. You want the smallest whole number ratio of elements. Now, the way you do this is you assume you're starting with 100 grams of the compound. And you're going to essentially take the mass of each element, and I'll give you an example of that. You're going to convert it to moles. Now, the interesting thing with empirical formula is it may not be the same as empirical formula. Or did I just say that wrong? Here we have hydrogen peroxide, which is H2O2. And notice that its molecular formula is much different from its empirical formula. Its empirical formula is the smallest whole number ratio. Here, molecular formula is not the smallest whole number ratio. Okay, so the molecular formula, the difference between that and empirical is that with molecular formula, we're looking at the actual number of atoms in the compound. So empirical formula, we divide it by a ratio. So notice with H2O2, there's 2 of each atom. If we divide the whole compound by 2, we end up with HO. So please note that a molecular formula is always a whole number ratio of the empirical formula. It may be 1 to 1, it may be 2 to 1, it may be 3 to 1, and so on. So I'll show you an example of this. Okay, so here we have propane, and it has carbon and hydrogen only. They say we have 81.82% carbon, 18.18% hydrogen. What is its empirical formula? The first step with this kind of problem is you're going to assume that you have 100 grams. So remember how I said you want to assume you have 100 grams. And you're going to take each percentage in its decimal form and multiply it by 100. And when you do, you get 81.82. Now, you want to calculate the molar mass of each atom. And when you do that, you're essentially taking the mass of the compound for that atom divided by the molar mass, and that gives you the moles of carbon or the moles of hydrogen. Now, once you've done that, this is key, you're going to look for the smallest number. So you're looking for the smallest number of moles. When you do that, you're essentially going to take each mole and divide it by the smallest number to give you a ratio. Now, this is where it gets a little tricky. We've got 1 mole of carbon, but notice we have 2.6 moles of hydrogen. So we can't use this as our empirical formula. It has to be the smallest whole number ratio. So what do we have to do? We have to multiply both by 3, and when we do that, we essentially get C3H8. So that would be the smallest whole number ratio. So please remember, you start off with 100 grams, you divide each percentage in its decimal form, you multiply each percentage in its decimal form to get a mass. That mass you divide by the molar mass of each element. You look for the smallest amount of moles, and then you essentially divide each by the smallest number of moles. However, if you don't have a small whole number ratio, you may have to multiply it by a factor. Here's another example where you have a compound that has C, H, and O. When you look at the ratio of atoms, it's 1.5 to 3 to 1, and that would not be acceptable for an empirical formula. So in this situation, you would have to double the amount of moles. Okay, so this is a nice flow chart because this will help you with any kind of problem solving. When you get percent composition, you want to express it in grams. You're going to take the mass of each element, divide it by the molar mass. You're going to look for the ratio of the elements. If they're all whole numbers, you've got your empirical formula. If they are not whole numbers, you may have to multiply it by a factor, and I would start off with 2 and work your way up. Once you get the empirical formula, they have to tell you what the experimental is, and I'll give you some problems in class about that. And you're going to divide it by the mass of the empirical formula, and that'll give you some factor. Once you've gotten that factor, you apply it to the empirical formula. And the empirical formula, if it's a 1, it should be the same as the molecular formula. If it isn't, empirical formula is going to be different than molecular formula. Okay, this is our last section of this chapter, and here we are going to talk about hydrates. Now, what is a hydrate? It's essentially a compound that has water molecules that are bound to a central group of atoms. And when we are looking at hydrates, we have to look at the number of water molecules. So there may be just more than one. There may be 2, there may be 6. In this situation here, at the bottom here, we have sodium carbonate, and we have 10 waters that are attached to this molecule, or this compound, I should say. And because it's 10, we call it decahydrate. So we need to use prefixes when we are naming hydrates. Your book does a great job of summarizing the prefixes for hydrates, and if you need to make flashcards, you probably should. So di, tri, tetra, penta, all the way up to deca. So you're going to need to know those prefixes, because I could give you a formula like iron 3 phosphate, and you have to tell me that it's a tetrahydrate. So you will be responsible for nomenclature. Okay, now, how do you determine a hydrate formula? In order to do that, and we should be doing that in lab, you need to start off with the hydrate, and you essentially heat it up, and then you subtract the amount of mass that you lost between the hydrate and the anhydrous, or the non-water bearing compound. And let's go for a formula or a procedure here. So you start off with a hydrate, you heat it, you weigh the anhydrous compound. So after you've cooled it, you subtract and you figure out the moles of water. Once you figure out the moles of water, you're going to look for a ratio. So you have to calculate the moles of anhydrous first before you look at that ratio. And once you divide the two, you're going to find that there's a number that essentially becomes the prefix of the hydrate. So here we have a hydrate, which is cobalt 2 chloride. It's been heated, and they have a certain mole of anhydrous chloride. So here you take the anhydrous chloride, and notice you're using molar mass. So you have to figure out what the molar mass of cobalt 2 chloride is using the periodic table. So you've got the mass of that. And notice you want to subtract it from the original amount, and this gives us the mass of water. So here we have 2.51 grams of water. Once you get the mass of water, you're going to convert it to moles of water. And trust me, you'll get very good at figuring out the moles of water. So the molar mass of water is 18.015, and that gives us the moles of H2O. We're not done yet. We're going to take the moles of water divided by the moles of anhydrous, and that gives us a ratio. And the ratio is 1.95. I'd round it up. And essentially you would write it as cobalt 2 chloride dihydrate.